Mm-hmm. 2, 6, 10, 14.
2, 6, 10, 14. Lovely. What is an atomic orbital? Somebody else? So this would be 2, this would be 6, this would be 10, and this would be 14. Right? Atomic orbital. What is an atomic orbital? Somebody else go. Kadeen, Jade, and Jane, Chelsea, right? Anelia, Amal, you guys are here. Have a go at a question. What is an atomic orbital? You guys should be able to answer that. Go ahead. Shini.
Okay, so the space around a nucleus where you have a high probability of finding an electron of a specific energy.
Lovely. Beautiful. An area around a nucleus, right? Well, yeah, area around a nucleus, right? Or a specific region in which we have a probable electron location and or there's a probability that we can find an electron. All right, lovely. Right, we must be able to draw the 2s and 2p orbital. I'm just going to assume that we should be able to do that. Right, if we're looking at, let me that line on the screen. No. All right, so if we're looking at something like that, what we generally can have a look at is not this, but how these are looked, right? So this is how generally the orbitals look. So the s orbital, right, is spherical in nature. But what this diagram is showing, this is a probability diagram, by the way, right? It shows that there are probabilities of finding an electron around the nucleus itself, right? And it tends to provide this spherical region, right? With the 2s, they're going to have one electron density in there. They're going to have an area of no electron density. Then you're going to have high electron density around it, right? That's going to be for the 2s orbital. And for the p orbital, you're going to have a dumbbell shape. And we know we have pz, py, and px orbitals, right? So you guys need to know how to draw your orbitals. All right. Any questions about drawing the orbitals? Any issues with the orbitals? All right. Going once. Going twice. All right. Back to the questions in which we're looking. Let's get back to these questions down here. Right. Okay. Write the electronic configuration for the following atoms and ions. For the copper plus atom, go ahead. Could somebody have a go at that?
Question, sir. When they ask us to draw like the p orbital, should we draw all three or is one fine?
You
Sir.
okay? I tend to actually draw all three on their different axes. Right. That's what I tend to do.
Sir.
Go ahead. Somebody said, sir. All right. Okay, go ahead. Somebody raise your hand.
Sir?
Yeah.
Sir, you want us to answer the question?
These questions here, the electronic configurations, yes.
Yes.
Atoms and ions. So please have a go at all of them. Right. To make sure that this makes sense, I'm going to set a timer. Right. Should I set a? Let me not set a timer. We're just gonna go through them. For copper, what do we think? What do we normally do for these? Can somebody explain to me how we go about these questions? How do you go about it? Go ahead.
Sir, instead of writing out the whole 1s 2p thingy from start, then you would just write the standard element in bracket that you would use to represent like a certain amount of electrons. For example, argon, which is representative
Why
of
we use
18
argon?
electrons.
Why we never use helium? We could have used potassium as well, you know. Oh my gosh, we could have used sulfur. But why we use argon? We
So,
tend
because it's the closest noble gas.
because it's the closest noble gas, right? So yeah, Miss Hu was completely right, right? And we tend to use noble gas, noble gases to show all of those, right? It's mainly because they end out the S block, right? Can you guys see my wallpaper? No, you guys cannot. Let me change how I'm sharing real quick. I want to share my entire screen because my wallpaper is just a periodic table, interactive periodic table. So give me a second. Let me share everything and we'll go through this. Alright, hold on. My entire screen. Alright. So we have this here. So everybody can see my screen now. Just let me know when you can see it actually. You can see it?
Yes, sir.
Alright. So we have S block and P block and D block elements, right? And we also have F block. Our F blocks would be our lanthanides and actinides down here, right? Our lanthanides start at 59, which is 57, which is lanthanum, and 89, which is actinium. Don't care about F block, right? So our S block will be hydrogen, right, along with the rest of the alkali metals and the alkali earth metals, right? The alkali earths. So why are they called the S orbit? The S block. Anybody know why?
Because we get up to 4s orbital or 3s orbital.
Alright, so their largest orbital tends to be around their last orbital tends to be the S orbital, right? Here in the P block, the last orbital tends to be the P orbital, right? So what we tend to do, right? We tend to get the most stable arrangement, right? Which would be our noble gas arrangement, right? We write out that arrangement first, and then we move into writing all the other residual electrons, right? So if we're going to be writing something like boron, right? What we could do to represent the entire period before is write helium and then make up the rest of the electrons to boron. So that's what we're doing, you know. If we're gonna be writing copper, right? What we do, we write argon, right? Which basically represents all of period 1, 2, and 3. And then we write up the different electrons that bring us up to copper, right? So that's basically what we're doing. So writing the noble gas is basically to account for all the configuration that came before, and then all we do is write the rest of the electrons that will bring us to that element in that period, right? So if we have copper, the noble gas that comes before copper is argon. We know that. All right, lovely. Argon has a mass of what? What's the mass of argon?
18.
18, right? So we have 18 here. So argon is worth 18 there. What is the mass of copper?
29.
Repeat. 29. All right.
Yeah, 29.
29, right? And then when copper plus now would be what? 28, right?
Yes.
28. So what I tend to do, my procedure is that once I find the amount of electrons that should be existing, I minus the noble gas, the noble gas configuration. So if you minus the 18, right, from 28, right, what is it we're going to get? How many electrons we should provide?
10.
Should provide 10 electrons. So we start off from argon. What is the next orbital that we're going to be looking at? Which orbital will fill first? The 4s orbital? So we're going to say 4s2, and then we're going to have our 3d orbital. 3d what? D8, yes? That makes sense?
3D8.
Lovely. 3D8. So that
Yes,
would
sir.
be lovely. So that would be our electronic configuration for our copper plus, right? For scandium now, scandium's atomic number is, what would that be?
21.
21. That's what I say. I keep asking questions. No, 21. Is it really 21?
21.
I don't know. Alright, so it's 21. Why does it sound like we don't know? Right? So it'd be 21. The noble gas that comes before scandium is also argon. Right? So we're going to minus 18 from 21, which will give us. Which will give us what? Never heard that twice.
3.
Alright, so 18 from 21 would just give us the 3 that we want, right? So what's gonna happen here now? We're going to end up with what? 4s, 2, 3, d, 1. That is scandium, yes? Right, so it's the same thing like that. So for oxygen and iron and phosphorus and the chromium and the nitrogen, the titanium and the manganese, right, these will all go through that same. That is the procedure that I use. So the noble gas that comes before oxygen is not argon. Right, what would it be? The noble gas that comes before oxygen is what? If you look at this, oxygen is here, so it'd be helium. So I would write helium in the bracket and then work my way up to oxygen. Right? If I was working with the phosphorus there, right, I would write my neon and then work my way up to my phosphorus. Right? So I'm not sure if we need to spend any more time really on doing that part. Right? But we should be able to really be answering these, right? We should be able to go through this stuff and handle these electronic configurations. Are there any questions or concerns that we need to be aware of before I continue? Before I move on?
No, sir.
Alright, no. Anybody else? Everybody's cool with electronic configurations and drawing your orbitals and stuff like that?
Yes, sir.
All right. So as it relates to doing arrow diagrams, right? We know that we follow Hund's rule and Aufbau's principle, right? So please follow your Hund's rule and Aufbau's principle when you're filling electron shells, right? What is Hund's rule? Could somebody state Hund's rule for me, please? Let me go here. What is Hund's rule? There are 3 rules: Aufbau's principle, Hund's rule, and the Pauli's exclusion principle. 3 of them when we're talking about filling electron orbitals, right? What is Hund's rule?
Sorry, it's not on this syllabus, so we didn't learn this.
Oh, it's not on the syllabus. Oh no. My apologies. My apologies. This is why.
Sir, we learned some rules, but like,
Okay, so the rules that I learned, those are what they are called. The Aufbau's principle states that we must fill a lower energy orbital before we fill a higher energy orbital. Makes sense, right? Because we can't fill 2s before we fill 1s. Make sense?
Yes, sir.
Right? Aufbau's principle. Wow. Right? Hund's rule states that if we were filling an orbital specifically, right? Just follow closely. For every orbital of a subshell, right, it is filled with a singly occupied electron that has the same spin. What that mean? If we're filling the 2p, right, we can't fill it like this. We can't fill it like that going across. You'll never see that, right? What it will do is fill with 1 electron in every orbital and then pair them up. Makes sense, right? So that's what the Hund's rule is. The Hund's rule states that if we're filling a subshell, right, we must fill all the singly bonded, well, not really singly bonded, the single pair the single electrons, right? Let me not say single pair, single electrons, right? We put all of them in the orbital first. We fill it like that. That is what Hund's rule is saying. And what the Paul exclusion principle tends to help us to explain is the difference in ionization energies across the periods, right? Different blips, right? But what we're generally talking about is that the spin must be different. If we have an orbital, the spin of both electrons within the suborbital, right, must be different. So one must be an up spin and one must be a down spin. Alright? So that's generally what we use at this level to simply explain that with Pauli exclusion principle. Right? That's Pauli's exclusion principle there. So we follow Aufbau's principle. The fact that we need to fill lower energy levels before upper energy levels, right? Hund's rule states that we don't pair up electrons unless all the orbitals have at least 1. So we add the electrons of an electron into every subshell, and then we continue to pair them up. Pauli's exclusion principle states now that when you're pairing up the electrons, they must be of opposite spin. Make sense? Make sense, guys?
Yes.
Alright. And that is it.